Okay, Bismillahirrahmanirrahim. Welcome back, everyone. So here we are, resuming our course from where we left before the lockdown. So here we are. So there are a few things before we actually start that you should consider now. First thing, um, from now on, there will be online lectures on YouTube like this. The numbering of these lectures will be from number one from this lecture until the and from here on. So the numbers will be continuing from 0, 1 to the last one, that will be around 17 or 18 lectures that will be doing now after this break. So over the next three lectures, the first three lectures will be mostly about the refresher part. We'll be doing a bit of revision of the whole course that we have done already. So starting today, starting the first part of this refresher one, so we'll be doing Boolean algebra. So it's actually just a revision part. So and the whole thing about Boolean will be done in this today's lecture. So you have to be very you should be you should have the idea about most of the things. Just the basic idea of the today's lecture is just to refresh those concepts that you already studied during the regular course. So what will be run? We'll be doing the step by step. The first part is Boolean algebra. Then we'll be doing some K maps and combinational logics, and also then or logic circuits before actually continuing further in the course. So today is the first part where we'll be doing the Boolean algebra. So here we are. The first part of the Boolean algebra that we actually did was basic operations, and that means the most common basic operations of Boolean algebra are and, or, and not. So we know these three are the very common Boolean operations. So these are and, or, and not. So here we are. The truth table for and is basically for two input AND gate or any input AND gate. We know that the AND gate or AND operation, the output will only be high when all the inputs are at logical high level. So it means if all the inputs are 1, the output is 1. Otherwise, if any input is 0, it means the output will be 0. So it will not be logic high in this scenario. For OR, what happens if any of the input becomes 1? If any of the input becomes high at high level, the output will become high. So it means the output will be 0 only if all the inputs of are actually 0. So if all the inputs are 0, the output will become 0. Otherwise, if any input is 1, the output will become 1. So uh, the third operation, the NOT gate. The NOT operation is not the binary like and or. It's basically a unary operation. That means the input is a singular input which will be complemented. NOT is a complement. Complement means if the input is 0, the output will be 1. The inverter is also called an inverter. So if the input is 1 or logic high, the output will be logic 0. So we know the logic gate symbols for and, or, and not as well. So the next thing, we know that we can build any circuit, any digital logic circuit from any Boolean expression by connecting different gates, different logic gates in an order. We can get anything. The example circuit below, it's simply x plus y prime and with x plus means here we know that plus is basically or, and simply dot or you can say simple dot or multiplication was now in the Boolean algebra it's used as and. So it's basically x or y prime and with z or x prime. So this circuit here you can see this is your x plus y prime, y naught is basically used in this OR gate. X plus the output of the OR gate is x plus y inverter. So this is one thing. The second one is x bar. X bar is simply the invert of x. So this is the second inverter that you can see here, and output, the OR gate output x plus y inverted. It is basically AND with that. So this AND of AND gate is x plus y bar y prime, and with that, and the both the output of AND gate and the X inverter is entered into this OR gate, and the result is your final expression that is given in this circuit. So the next thing, the last page circuit is actually not a very simplified circuit. So it's basically the first principle of logic circuit is it has to be a simplified circuit. Simpler, it should have the minimum number of gates required to complete the task. So simpler hardware is almost always better. In many cases, simpler circuits are faster. Less hardware means lower cost. A smaller circuit also consumes less power. So actually this is a very small circuit, but in simple digital computers or digital devices, you prefer to have as simple circuit as possible. So how to do the simplification, how to simplify thing, that what we studied in the Boolean algebra. So you can use the Boolean algebra just like a simple logical, simple mathematical arithmetic algebra. The Boolean algebra is very similar. You can use the identities, the principle, the properties of algebra to actually simplify the expression. So here are few axioms or properties that are used in Boolean algebra. You can see here uh, x plus 0, OR gate with x. If we do the OR operation with 0, the result will be the same, and that we know. And similarly for AND, if you do the AND operation with 1 instead of 0, the result will be the same. So this is like the additive identity or identity, or remember when we studied additive identity, if we add anything with 0, the result is the same. Similarly, if we OR anything with 0, the result will be the same number. It's the same logic value. So x plus 0 will be equal to x, or 0 will be equal to x, and x dot 1 will be equal to x. This is for AND. So similarly for OR, if we do an OR operation with 1, the result will always be 1, because we know that well, whatever the value of x is, it will not matter if it's being OR with 1. So similarly, if for AND operation, if we AND something with 0, the result will always be 0. If we because we know that you have to have both values 1 to make it count. So similarly, x plus x or x will be equal to x, and similarly x and x will be equal to x. So these are a few basic things. X plus x bar, x prime will be equal to 1, because if x is 1, x prime will be equal to 0. So 1 plus 0 will be equal to 1. If x is 0, then x prime will be 1. So either case, the result will be 1. And if we are doing the same thing with uh, AND operation, if we are doing x with x prime, if x is AND with x prime, the result will be equal to 0. Why? Because if x is 1, the x prime will be 0. So obviously one of them is 0, means the result will be 0. So similarly, there are commutative, associative, distributive properties that we studied. There is one major difference from the typical arithmetic. Commutative property is simply x plus y is equal to y plus x, x y is equal to y plus x. It will satisfy things just like the arithmetic operation. Similarly, associative, x plus y plus z is equal to x plus y plus z. So the order of the operation will not matter, both in OR or AND. So in both cases the order doesn't matter. That there is one difference in the distributive of and our or is just like multiplication or addition. We just open the bracket and do the and operation with every uh, individual variables. But for distributive of or our and, this is something that holds true for the Boolean algebra. That is actually not possible in simple arithmetic algebra. In simple arithmetic algebra, you cannot do this something distributive property of addition or multiplication. So that is not possible for uh, your typical arithmetic simple algebra. So this is something different from your normal one. Similarly, there is a De Morgan law. De Morgan law, you actually convert from the same expression on the left hand side. If it's an and and operation, the right hand side will be the same, will be done using the or gates. And similarly, if the left hand side is or, the right hand side will be in and. So x plus y, x or y whole complement will be equal to x complement dot y complement. So or an or operation whole complement is actually opened up with both inverted, and it becomes and operation. Similarly, for if 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 you have got on the left hand side an and operation and whole invert, it will be opened up with individual inverted, but the operation will be or in this scenario. Let's just go through these again, just do a quick refresher for that. So satisfying the axiom, we know that we can actually prove using simply truth tables. We can get those identities verified using the tables. So simply we can show that the axiom x or x prime is equal to 1 always hold. We know that there are simply two values, x prime, and this will be true always. So and similarly we can have all the possible options for any case. We can satisfy those. So we know that there are few similarities that actually I already talked about in the previous slide. The same things. It's just like the typical regular algebra, but it's actually Boolean. Few things are same, just like the same. Few things are different, like the one I actually mentioned. There are few operations which are actually different. So the magenta axiom deals with the complement operator. Here we have got few simple operations which are actually make use of the complement of NOT gate. So you can actually if you want to understand further, you can use the same example in English as well. So like x or x prime is equal to 1, it means you can actually compare it with an English example that it is snowing x or it is not snowing. So either it is snowing or it is not snowing, both the cases they will always be true. Either it's snowing or it's not snowing, so it means that both of them will always be true. Either it is snowing or it's not snowing, so that's why it will always be 1. Similarly, x dot x bar is equal to 0. It means it is snowing and it is not snowing. It cannot be possible that it is snowing as well as it's not snowing. So either of the two, either it's snowing or it's not snowing, they cannot happen at the same time. So that's why it will always be 0. That can never be true. So similarly, if x prime whole prime is equal to x, so if it you are actually negating some expression, I am not handsome, that means I am handsome, because you are actually negating the not by putting another not again. So if you are doing not handsome, so it means the both not will be cancelled out. So these are very simple things that you actually have some idea. So we also studied about De Morgan law. What is De Morgan law? De Morgan law explain how to complement the simple arbitrary expression. Here are simply you can actually write these De Morgan laws in English as well. So you can say if X is I am rich and Y is I am famous. So I am rich or I am famous. So basically, I am rich or famous. So you are basically doing an or operation and negating the whole one. So it means I am not rich or famous. So rich X is rich, Y is famous. So it means rich or famous. If you are saying I am not rich or famous, it's actually the same thing is or as I am not rich and I am not famous. So basically it's simply the same expression. If I am not rich or famous, it's the same thing as I am not rich and I am not famous. Similarly, another thing, I am not old and bald. This is the second one. X and Y for prime will be equal to X prime or Y prime. So you can say if X is old, Y is bald. I am not old and bald means old and bald. Both old and bald have to be true. I am not old and bald means I am not old or I am not bald means either I am not old or I am not bald. But I could be one, young and bald. You can be bald but not old. You can be young and hairy. You can be you cannot be um, you can be not old and not bald. So it means you can be young and hairy. And similarly, you can be old and hairy, old and not bald actually. So these are simply simple expressions to understand how the De Morgan law work. So this is just a simple thing you can use in your simple logic expression. You can use simple De Morgan law to simplify a lot of things, a lot of circuits using these laws. And other differences from the regular algebra that actually we just talked about, like simple x plus 1. In simple addition, you cannot have the value 1. You actually add these, but in logic it's always 1. So anything, and similarly, if we are doing you are doing an or operation with 2x, it will not be 2x, it will be either x. And similarly for if we are doing AND operation with x, it will not be x square, it will be x. Why? Because we don't have the further thing. Similarly, the distributive property of or our AND is actually something, and this is actually used in a lot of, you can use it in your expressions to simplify things, but they are not, it's not possible in simple regular algebra. So you can simplify any expression using these algebra, using these uh, different different axioms, different properties to get the simplified expression. I think we have done a lot of examples using these properties to simplify things, and you know how these things work. So just moving on from here. Simple expression yields simpler hardware, the same circuit, x bar y bar plus x y z plus x bar x prime y. The whole circuit is actually the same circuit as x bar plus y x prime plus yj. So this is actually the simplified version. How we simplified it? We simply use the commutative property first, and then use the distributive property, and then using this simple property of to get this expression. Finally, this whole three term expression is actually simplified into this expression where we just need three gates here instead of 1 2 3 4 5 6 gates. So you can always do the proof with truth tables, um, instead of just going through all the steps in expression. You can also do the simplification using simply truth table, but there are different steps that are involved. You can always check your expression, your simplified expression with your tables, and you can see here it's exactly the same thing. So here is this is actually the truth table for Morgan law. So you know that both of the cases it's actually the same thing. Okay, there's another thing that we studied. It's called duality. So there's a reason why the table of axiom has two columns. Why the laws on the left and the right are duals of each other. You know that if we have got an OR operation, x or 0 is equal to x, it actually has got a dual x and 1 equal to x. So basically the result is the same, but the expression, the operations are interchanged. So basically what happens in duals, the and or operators are exchanged, and actually the constant values, if there are constant values, if there is a 0 or 1, they will also be interchanged. If we are doing the simple OR operation with 0, so it means we will be doing the AND operation with 1 instead, and the result will be the same. So similarly, dual of any equation is always true. If E and F are two equivalent expressions, the dual of E will also be the equivalent to the dual of F. So this is how it is. So how to get the dual? We just do one little thing, just replace the constant, just interchange the constant, replace zeros with ones, and do the replace and with or, and vice versa. It will get you the dual of that expression. Similarly, there are some more laws, some other useful equation that we can do. X plus xy is basically, you can simplify this expression with you simply taking common. It's basically uh, x into x and x plus y, which will be equal to x. So basically you can use the simple distributive property to do this. So you can use these in different assignments that you will get. So these are different expressions to simplify this. So why is it called Boolean algebra? Basically because of the person, the scientist who actually invented it. It was the Boolean algebra was invented by this scientist called George Boole way back in 1850s. Obviously, back then there was no digital computers or stuff, but and it wasn't until 1937 that actually this another scientist called Claude Shannon, he actually got the idea to apply the Boolean algebra to circuit designing. So it actually came to circuits much later, but it was there in the 19th century. So how to complement a truth table? If we have got a three, let's have this example. We have got a truth table with a three expression in three input x, y, and z, 0 0 0 to all ones. This is on the right. This is a function f of x, y, and z. 1 1 1. These are the values. If we just do the complement of this expression, what we'll do is, or we'll be replacing all the ones to 0. Why? Because it's actually simply on the right in the table for the complement of f, it's just a simply invert of f. How to complement an expression? If we get the value here, for example, f is basically x plus y prime into that's the same expression plus x prime. This was the original expression f. How to get f prime here? We just simply we can do the we can simplify this expression by doing the whole complement of the whole expression, and the result the expression that we get after the whole simplification, that will be the value that will actually satisfy the second table that we have got, x prime y plus that prime, and with x, that will be the second table. It will actually satisfy the second table. So another clever method of complementing an expression is to take the dual of the expression and then complement each literal. So duals are very actually good things. If we know how to simplify things using duals, it will be much easier. What you do is you just simply take the dual of the expression and then complement each literal. So it's just like the De Morgan law. So De Morgan law is basically, you can say De Morgan law is just dual of each other. What you do is make a dual and complement every literal. Okay, then we actually studied about the sum of product terms. It's basically all the and terms we have got in a expression for a specific number of inputs. Here we've got x, y, and z. We've got three inputs. It means that for x, y, and z, these are actually three different and terms, and there's sum of these are simply OR gate, or you can say the addition sign in between them. So it means we have got three terms, the three AND terms, and we have got two all of them as an the output is OR. So we can actually implement a sum of product term as simply OR gate at the end, and as input we will have different AND gates. So if you've got three terms, we will have three AND gates, and we've got one OR gate as a function to do the sum of all these AND terms. So it's simply a two-level function here, because we have got in the first level the AND gates, the second level we have got OR. So the zeroth level is where the complements are done. So this is something which is actually very helpful in getting the expression using the other method. For that we actually use the term minterms and maxterms. So what is minterms? Minterm is when all the possible AND terms in a typical scenario. So for example, with n inputs variables, if you have got three input system x, y, and z, it means we'll have 2 raised power n. That means 2 raised power 3, 8 possible minterms. So if you have got three inputs x, y, and z, it means we will have 8 possible minterms. Similarly, for x, y, and z, it will be minterm 0, which means all the inputs are 0. So similarly, 0, 0, 1 will be a minterm 1, M2 will be 0, 1, 0, M3 will be 0, 1, 1, and up till M7. So this is just like your whole truth table. All the possible values are here: M0, M1, M2, M3, M4, M5, M6, and M7. Why? There are 8 because we have got 3 inputs. If we had got 2 inputs, we'll have 2 raised power 2, 4 possible minterms. If you've got 4 inputs, we'll have 16 possible inputs. So sum of minterm expression, we can write any expression by just writing the sum of minterms for that specific term. If you got a C, we know that these are 1, 2, 3, and 4. We've got 4 minterms. We can just simply write the summation sign of M, 3, 5, 6, and 7. Basically 0, 1, 2, 3, 4, 5, 6, and 7. These are the 4 minterms that are used here. And similarly, if we want to write C prime or C inverted, it will be the same. Those where actually for C, where the value of 0, the value of C was 0, it is now 1. So it means the sum of all those minterms where the C was 0, so it was 0, 1, 2, and 4, it will give you C prime. So C prime contains all the minterms not in C, and vice versa. So if we can write any expression using their minterms only, this will be helpful in simplifying in using some other ways. Just like minterms, there's another thing called product of sum terms. So it will be another similar type of circuit. It's another two-level circuit, but it will be different than sum of product. Why? It will be product of sum. It means that last stage, the last level of this will be an AND gate, and before that it will be a whole level of OR gates. So all the all the sum terms will be you, the sum term means there will be OR gate for each sum term. So if we have got x plus z will have a OR gate. X bar plus y plus z bar, it will have a OR gate for that. So the same expression g x y z is actually y prime, and with x prime plus y plus z prime, and with x plus z, it will be this will be the same circuit using the two levels. The first level is simply inverters. First level will be zeroth level is inverter. First level will be OR gate. Second level will be AND. And just like minterms, those terms, the sum terms, they are called max terms. So max term means x plus y plus z. It will be if they are all of these are zero, it means it will be capital M 0. Similarly, capital M1 will be when x plus y plus z. So x is 1, y is 1, z is 0, it means this will be M1. And similarly, till x bar, x prime plus y prime plus z prime, this will be M7. So the same thing is actually done. You can write the same function as product of maxterms. So how to write product of maxterms? For product, we have that product sign, just like the summation, we use the pi sign for product of max terms 0 1 2 and 4 for C, and similarly for C prime we have got the product of M, capital M, 3 5 6 and 7. That means the product terms of the product terms or maximums of 3 5 6 and 7 will give you C prime. You should notice one little thing, that it's actually the similar thing uh, with your min terms, but you should notice that the min term for C is actually max term for C bar. The same uh, the same thing, but it's actually inverted. So this is actually the dual property that can lead to min terms and max terms are usually duals of each other. So now we have seen the two different ways to write the function C as a sum of min terms, or uh, as a product of max terms. So notice the product term include max number whose corresponding min term do not appear in the sum expression. It's just the opposite of that. It's just like the min terms of C prime is actually in the max terms of C, right? So this is something that that is helpful. That relationship is basically it's more like the dual. So min term is when all the inputs are 0 0 0 0 is M0. The max term will be when all the M0 will be when all the inputs are uh, it will be false only when all the inputs are 0. So technically it's just simply OR gate or operation of x plus y and z. So x y z it will give you basically the 0 output will actually decide the max term value. So x plus y plus z, if all the inputs are 0, the output will be 0. If any of them is 1, that means it's actually going to be it will not be this one. So you can actually simply convert from between the standard min term to max term simply using the same algebra, you can use the dual or De Morgan law to get the if you simply get the De Morgan law, it will give you the conversion from minterm to maxterm. The easy way to replace minterm with maxterm using the maxterm numbers that do not appear in the sum of minterm. So technically C is the same thing, sum of minterm 3, 5, 6 and 7, or product of maxterm M0, 1, 2 and 4. So they are just you can simply write these numbers as M0 plus M1 plus M2 plus M4 is C prime, and that thing is if you do this in max, then it will give you the value. So you can simply write this okay. We should have done some little example of the same example. You can actually write more convincingly here. Okay, from this table. Okay, here we are. So let's just analyze this number, this truth table, x, y, and z. See, if we want to write this expression in product of in sum of product terms or sum of max min terms, it will simply be x bar y z. This is m3 plus m5 plus m6 plus m7. That means we are doing the simply OR operation of for the different expression, different terms. If we do the same thing, if we just write the what we do is we simply do the De Morgan law of this number. What happens? We will have okay, it's actually not about this one. This will actually see the same C in product of sum term. So we don't have here C bar. Let's just see here what's happening in product of sum term, product of max term here. X plus y plus z. This is 0, m0, then m1, m2 and m4. So we are just doing the same thing, the product of max terms here. Just do one little thing. Let's just get C bar from here. How to get the C prime? Just do the simply De Morgan law apply or get the dual from this here. What we do is when we do the De Morgan law, you will actually get the max the max term of which max term will get from these values. So this whole number, this will be, this is 1, this is second, this is third, this is fourth. We have got these 4 terms here. We are doing the simple De Morgan law to apply on these 4 terms. What we do, what happened there, this will be simply prime, this is prime, so all these 4 will be, because we are doing the whole we are applying De Morgan law. So So in the end, what we'll get is the C prime will be simply the product of max terms. Which max terms? The same max terms. 3, 5, 6, and 7. That is something that actually we studied in these next slides. So if we are doing the simply, we have got the expression for C. If we just do the complement of it and expand it using the De Morgan law, we'll get the values, which the same values, but will be the product of the same max term will give you the C complement. So if we want to get C from here, it will be the opposite one. So these are the product terms for max term for C in this scenario, right? So here just this was just a bit of uh, your revision for these topics about basic Boolean algebra. I hope you actually have the basic understanding that we studied in the course, the regular course. So it was just for refreshing your memories. So we'll be doing a bit more in the next few lectures as well. So in the next lecture we'll be doing about your K-maps, how to simplify using K-maps instead of Boolean algebra. That's also that's something we have already done before. So you should have that understanding